Welcome to this summary video for Diploma Program Physics, where today I'm going to talk about topic 4.1, simple harmonic oscillations, which is fundamental to wave motion. And I'm going to exemplify this with a mass on a spring. And the mass has mass m, and it's displaced a positive distance downwards, and then we let it go, and it will go through the equilibrium position up to the top, down through the equilibrium position again, and then back down to the bottom again. Now let's plot its displacement against time. So in the beginning it's going to have maximum displacement here, then it's going to go down through the equilibrium position, it's going to have zero displacement, then it's going to have a minimum displacement when it's at the top, then it's going to go back through the equilibrium position and then back to its maximum displacement again. Now if we was to plot using, for example, a program like Tracker, all the displacements as time and then join them up into a smooth curve, the displacements could actually be modeled using a sine wave, and we call the time it takes to complete one cycle a period, capital T, one period. The time it takes to complete one full cycle. Now if we plot the velocity, since velocity, the instantaneous velocity is the gradient of the tangent to the curve of the displacement time curve, then the velocity is actually zero when it's at its maximum extension. And another word for maximum extension is amplitude. So its velocity is zero in the beginning, and then it's a maximum and negative as it goes back through the equilibrium position. So it's going to be, the velocity is going to be down here. Then at the top the velocity is zero again, and then as it passes through the equilibrium again, the velocity is maximum and maximum and positive, and then back at the maximum displacement the velocity is zero again. So the velocity time graph is also a wave, but it shifted quarter of a period to the left relative to the displacement time graph. Now if we look at the acceleration time graph, since acceleration is the instantaneous gradient of the velocity time graph, here where we have a minimum or a maximum in the velocity graph, we're going to have zero in the acceleration. So we have zero here and here, and the acceleration is maximum and negative here, it's maximum and positive here, and it's maximum and negative again here. So in each of these three graphs we can read off the period by looking to see the time it takes to complete one whole period, the time it takes to go from a minimum through a maximum and then back to a minimum again. Linked to the concept of period is the concept of frequency, which is defined as 1 over the period, or the number of cycles per second. Also for 4.1 regards simple harmonic oscillations, you have to know the conditions for simple harmonic motion and be able to interpret or recognize the acceleration displacement graph. So there's two conditions in order for simple harmonic oscillations to take place, and they're given by this formula here. Acceleration is proportional to the negative of the displacement. So the acceleration, or the force, has to be proportional to the displacement and directed in the opposite direction. So this result gives us a acceleration displacement graph which has a negative gradient and goes through the origin and is a straight line. And in the case of our mass on a spring, now I've just switched the mass on a spring system round to neglect gravity, but you see that if I displace it a positive distance here from the equilibrium, then the restoring force, the spring wants to pull the mass back again, and that restoring force is given by Hooke's law. The restoring force is equal to the negative of the spring constant times the displacement. So this satisfies this condition. If I was to put F equal to ma, and rearrange, I get that the acceleration is proportional to the displacement and the constant of proportionality is k divided by m, where k is the spring constant of the spring.